This is Toby Constein with the Energy Mashup Lab. Today I'm going to describe for you some open source software to operate microgrids and easily incorporate renewable energy sources. First, let me tell you a little bit about the lab. The Energy Mashup Lab is a nonprofit organized under 501c3 whose purpose is to develop and promulgate open source software for smart grids, especially microgrids. The lab was co-founded by David Cohen, a founding member of the Gridwise Architectural Council, and by software architect Bill Cox and by myself. Bill and I both worked on the first U.S. National Smart Grid Roadmap and then helped develop the essential information and communication specifications of smart grids and smart energy. In December 2012, I presented the paper, Understanding Microgrids as the Essential Architect of Smart Energy. My co-authors were Dr. Cox and Ed Cazalet. You may recognize Dr. Cazalet as the father of the modern transactive energy. In that paper, we described what is now termed fractal microgrids, in which every microgrid can be operated by a micromarket. Every microgrid may act as a node in a larger microgrid. Any node in a microgrid may itself be a nanogrid operated by a nanomarket. That paper is among the most requested and most downloaded in smart energy. Transactive energy names a means to coordinate consumers and distribute energy resources, and markets are means to coordinate private decisions for mutual benefit. Today, despite numerous trials, and numerous reports, and numerous proprietary systems, the promise of transactive energy is unmet. The promise of transactive energy is that of any service-oriented integration. That is, the rapid integration of systems, because participating systems do not need to know much about each other. Diverse technology support, because participating systems do not need to know much about each other. Rapid adoption of new technology, because other participants do not need to be upgraded to interoperate. Transactive energy also supports privacy and autonomy, because all systems are judged only by their effect on the microgrid and not on internal processes or internal decision making. Consumers in particular have not reaped the benefits of transactive energy. Fractal microgrids won't really be here until I can order an appliance over the internet, unbox it on Saturday morning, and have it fully integrated into my home microgrid before lunch. We've experienced new decades of trials and experiments without creating something that people can build around. So long as we keep changing the interfaces, there won't be any products. The architectural challenge is to isolate the volatility, that is, to encapsulate the things that we don't know and which will likely change. Then we can provide stable interfaces between those encapsulated components. The common transactive services are that stable interface. The common transactive services are a slim profile of the OASIS smart energy specifications. The largest, most resilient systems are built with the actor model. The actor model specifies many identical small systems that share only simple messages between them. Actors may have complexity and diversity internally, but they do not share it. Actors interact using only simple small messages and all use the same messages. As soon to be standardized, CTS is a minimal profile of energy interoperation, and more precisely TMICs. There are no special roles in the market. A power storage system, an appliance, and a neighborhood can all use the same simple messages. This slide shows a high-level conceptual look at the EML-CTS system. The diagram shows the interaction model of all actors communicating on a communication bus. All of the communication arrows are CTS. Certain nodes may interact with more than one set of peers, communicate on more than one bus, but such a node swallows that complexity. It interacts with its peers on each bus using only CTS. The CTS system is open source software for transactive energy. It's offered under an Apache 2 license for ready uptake and ready incorporation into commercial code. It is fractal ready because there are no special participants. It follows the actor model for high scalability and resilience. There is a complete separation of functions to enable interoperation even as technology and regulation evolve. It uses open interfaces, CTS for all interactions, and it works whether it's independent or grid connected. Dive into the components of the lab's open source software. Let's start with the local market. The local market agent receives all tenders, notifies participants of all contracts, and records all transactions. All database functions are isolated within the LMA. Changing databases or even using blockchain requires changes only within the LMA. The local market manager manages the matching engine or engines. different local markets may wish to use different matching engines, or even more than one. In EML-CTS, any such variations affect only the LMM. Now consider the devices, systems, buildings, and microgrids that participate in the market. All systems that can supply, sell, or trade power are considered TE users. Each TE user is represented by a TE user agent. A TE user agent communicates with the local market using only CTS. Note here that the external market, which may be a containing microgrid or potentially a traditional power supply or utility with tariffed costs and distribution surcharges, is represented only by a TE user agent. Each TE user agent appears as an identical actor in the market. All volatility of system and diversity of technology is hidden behind a TUA or within each local market or inside the LMA, or perhaps even in the matching engines within the LMM. All volatility of design and technology is contained. The actor interactions are all stable. The seminal research in transactive resource management was in allocating heat from a furnace within an office building at the Palo Alto Research Center, also known as PARC. The key insight was that markets could be built to determine the time of delivery for resources. Transactive energy is a particular case of transactive resource management. So what trades on the local market? Well, you can't trade resources. Resources are the commodities: power and energy, transport, ancillary service, network bandwidth, thermal, water and sewer. Products are chunks of resource. So power denominated in 10 kilowatt multiples over an hour is a product. A particular local market can trade in one or more products. A market instrument names a specific product at a specified time. Say, that same product delivered between 1 and 2 o'clock. The matching engine matches tenders to buy or sell instruments. Let us now look at the matching engine as a component. A market matching engine matches tenders to buy and tenders to sell to create contracts. Many TE trials have used double auctions to match tenders. EML-CTS uses an order book. Either model, and perhaps others, could be incorporated by changing only the local market manager. An integrator could even build a hybrid market, for example, using a double auction for day-ahead pricing and an order book for more current pricing. Any and all such variations would be enclosed entirely within the local market manager. The open source parity matching engine that we're using in EML-CTS 1.0 was developed for use in NASDAQ markets and can match tenders fast enough to support flash trading. Even so, it uses little memory and works on a small system. We are beginning to see the commercialization of nano data centers in a breadbox, developed for military use in places that get both far hotter and far cooler than we see in the US. It is not hard to imagine one of these being mounted alongside a transformer in a neighborhood. Work already done in NASDAQ and CME markets mirrors the matching engine, creating a hot spare with all tenders up to date to support active failover. EML-CTS does not support this failover yet, but when we do, it could be to another nano data center mounted alongside another distribution system transformer within the local microgrid. The components of the lab's CTS platform contain future technical and regulatory volatility while following the actor model. The remaining potentially volatile area is the actor fabric itself. EML-CTS is moving all network communications to a separate presentation layer. Today, it is encoded in JSON, bound to rest, over HTTPS. This encoding is ideal for debugging. This communication profile is appropriate for local communications inside a secure microgrid or nanogrid. So long as the messages remain limited to CTS, it could be encoded using any specification and bound to any protocol. Version 1.1 moves all actors into Dockers, adding full networking. This release will be complete this calendar year. Version 1.2 adopts from FinTech the fixed simple binary encoding at the application layer, designed to go faster and use less CPU for high-speed markets. We are adding some security and reliability bindings that have been developed as FinTech standards to support small isolated systems connected directly to the internet so they can participate directly in financial markets. This model is referred to as zero trust. The market can be anywhere, but we prefer it to be local for resilience and to support off-grid applications. So far we've discussed how the TEU agent supports the transactive energy user by interacting with the market. We haven't discussed how it knows what to buy or what to sell or what the transactive energy user wants. This rough schematic here shows some of the issues that will come up and how to think about it, but they're way beyond any architecture that the Energy Mashup Lab supports at this time. Still, we can see that there's various components that must be there. There's the devices, called here resources, which do what they do. There's some abstraction that says this will use this much power for this long when it operates. This thing must communicate up with an energy manager, which may manage multiple resources and the resource access. It may be responding to the owner and the owner's budget. It may have some situation awareness, understanding that it's cold outside or hot outside, and so has different cooling requirements. It may have some ongoing market intelligence it's gathered. Not all of this is outside the scope of the lab's architecture. But that said, it's all isolated. You can start writing things that do it today. You do not need to wait for the rest of the market for the other pieces to be fully assembled. Just so long as you can put a TUA in front of your device, then you can participate in the local energy markets. The purpose of the architecture and of the lab's software so far is to end the era of non-interoperable trials. There have been many transactive energy user trials out there and many transactive energy demonstrations. None of them interoperate. No device that's made for one ever can work with another. There is no way to build devices at scale. With this architecture you can, because all the functions are isolated. Makers of systems that produce consumer store energy, that is appliances, or building automation systems, or smart buildings, or battery storage systems, or home generators, anything that produces, consumes, or stores energy can use the same interface to interact with a transactive energy market. So start building your end user products now as TE users using the common transactive services. And let us know what you think and what needs to be added to the standards. This concludes the quick overview of the EML-CTS software. In the future, we'll have some background on how we develop the software, on transactive energy, and maybe some drill downs on some of the modules. Please subscribe to make sure that you get all the new videos when they show up, and have a good day.